Let's take a look at the scene that's new in Gravity Engine 6.0 called On Rails Moon to Earth. So we're here in the mini-games folder. There are two versions of this scene, one with dimensionless units and one with the Earth and Moon with the orbital units selected. So we'll work with the dimensionless units. So the intent of this scene is to compute the burn required to return from the moon to the Earth. And since that would be a three-body problem, because you have the spaceship, the Earth, and the moon, and that's a very detailed, twitchy problem to do completely accurately, this scene uses a patched conic approach to that. If you set up Gravity Engine in n-body mode and put in a specific burn, you will get the correct three-body path, but the actual planning of the maneuver is more complicated in that path and something that I'm leaving for future work. So let's just go ahead and take a look at how this patched conic scene unfolds. So we have in our scene the Earth, which is considered planet here, and a spaceship, and underneath the planet we have a moon. And if we go ahead and press play, it shows us a bunch of stuff which we'll talk about in detail, but if we go ahead and press X to execute the maneuver, we have a ship. We can press F2 to zoom in around the moon. We have a ship in orbit around the moon, and now that the maneuver has been planned, as the ship gets to the point behind the moon from the Earth, it then goes into an escape hyperbola. Then at the point where it reaches the sphere of influence, it transitions to an orbit around the Earth. And because this is on rails and using Kepler sequences, this entire process is completely reversible, which is kind of cool. So let's break down how this works and what all that stuff we saw at the start actually is. So we'll stop the scene there. So the thing that's drawing all of those circles and hyperbolas that you see while you're planning the maneuver is this script on rail moon to Earth. And the thing that it's doing is taking this escape velocity fraction here and using it to determine the velocity of the burn at the point where the spaceship is behind the moon. And it has references to the things you would normally expect it to have: the spaceship, the planet, the moon. It also has a prefab because it's going to create a number of ghost ships, and it will use these ghost ships and the orbit predictors attached to them to work out the different segments of the transfer around the moon. So let's go look again a little more carefully at how that stuff all works out as the scene runs. So we'll press play. Notice that we're reporting a particular periapsis up here, and that's the distance of approach from the Earth to the moon. If we change this escape velocity fraction, then that changes. So in this case, we get a trajectory that comes much closer to the Earth. That might be what we want for re-entry. And it tells us the scale of the burn in meters per second. So I'm going to press space and pause this scene. And then we're going to press F2 to look at this slightly complicated sequence of ghost ships and moons that are required in order to determine the correct trajectory. So there's really a multi-step process that we require. So the first thing that we need to do is figure out when the ship will be behind the moon. So as the ship is orbiting, the moon is also moving, so there's some code in the compute transfer logic of this on-rail moon to Earth that figures out how long it'll be until the ship is behind the moon. And then what it does is it creates a ghost moon at that location. So you can see there's this ghost moon TEI object, and so that moon is the position of the moon when the ship is behind it. And we place a ghost ship at that location and then apply the escape velocity change, and that gives us a hyperbola that then comes to this point here which is the point at which it exits the moon's sphere of influence. But there's a bit of a catch, because as the ship is flying along this path here, from here to here, the moon itself is going to move from this location all the way over to this location during that time. So when the ship actually exits the sphere of influence, we need to have moved the moon to that point. So we have a second ghost moon here, which represents the position of the moon when the ship reaches the SOI exit point. And then at that point, this ship, this ghost ship here, is given an orbit predictor around the Earth and given a velocity with respect to the Earth. So we need to we need to account for the velocity of the moon because it's moving with respect to the moon. So with respect to the Earth, you need the ship velocity plus the moon velocity. And then that orbit is the one that's predicted, and the closest approach of that orbit is this periapsis up here. The net result is we end up with a delay until we get to the point at which the ship is behind the moon. So our first orbit is just an initial orbit around the moon. We have a second segment that is the hyperbola, where we fly out to the edge of the moon's sphere of influence, and then we have a third segment, which is an ellipse, and that ellipse is around the Earth. So if we go ahead and press X in this scene here, and then we go and look at the spaceship, you can see in the inspector, if you look at this Kepler sequence, it's showing you that there are 3 segments and the times at which those transitions will occur. And all of this has been computed by the on-rail moon to Earth script. And it's the fact that there are these 3 segments that allows us to do the zooming back and forth. So currently we're in segment 1 here. And if we wish to, we can slide things forward, and you can see that we go to segment 2, and if we slide back, we're now back to segment 1 over here. So this scene shows how you can work through this. It seems like there's a lot of moving parts, and that's fair. There are a lot of moving parts. But if we look at the amount of code that's actually required to update all these ghost ships and do the correct calculations, it's done in the on-rails moon to Earth. It's compute transfer. So here we're at line 265, and we're done at around line 340. So that's about 80 lines of code. So it's not an insane amount of code. There's also a bunch of white space and comments in here. And what I've tried to do is comment very specifically how all of these factors are determined and how we're setting positions of the ghost moons and the ghost ships. We're putting them in Kepler orbits. We're locking them at particular times based on the evolution of the system. And then the result is the scene that you see evolving here.